Let's now look at the June 07 paper 1. There's a radioactive isotope of carbon known as carbon-14, atomic number 6 and mass number 14. We commonly refer to it as carbon-14. Complete the table below to show the number of particles in the nucleus of carbon-14. Now, be very careful, it's asking you about the numbers of particles in the nucleus. So, the atomic number tells us the number of electrons and protons, but the electrons aren't actually in the nucleus, so we have 0 electrons in the nucleus. The atomic number tells us that there are 6 protons in the nucleus. The mass number of 14 tells us the sum of neutrons plus protons. Therefore, neutrons is the 14 minus the 6, which gives us 8 neutrons. Fairly straightforward, 1 mark for each, but just be careful to read the question there. That's the number of particles in the nucleus. And it's even in bold there so that you don't miss it, but just be careful. That's the kind of question that could trip you up slightly. Complete the equation below to describe the process by which a beta particle is emitted from the carbon-14 isotope. Well now, beta, it's a fast-moving electron, so the mass of it is considered to be 0. Negligible, but we write in a 0. The charge in the beta is a -1. Now you must learn these symbols for alpha, beta and gamma radiation and their associated masses and charges. Now, an equation means that you must have an equal number on either side. So each side is equal. So the atomic number, which is 6 for carbon on the left, must be equal to the sum of the atomic numbers on the right. Now we've got a -1 here. Therefore, the nitrogen atomic number must be 7, because 7 minus 1 gives you 6. The same applies to the mass number. We have 14 on the left, therefore we must have a sum of 14 on the right. So it's going to be 14 plus 0 gives us 14 on the left. A mark for each of those boxes. Part B. A student states the following. After 2 half-lives of a radioactive substance have passed, its activity is 0. What is wrong with this statement? 2 half-lives. Well, let's think about what a half-life means. It means that the activity of the substance has reduced to half its original value. If you start out assuming that it's 1 initially, and it goes down to half, in the second half-life, then it goes down to a quarter. So what's wrong with this statement is that the activity will not be 0. Or you could have said there the activity should be a quarter, not 0. And what should it state? It should state that after 2 half-lives of a substance, radioactive substance have passed, its activity is a quarter of the original value. Okay. Moving on then to the next part of the question. The graph below shows how the radioactivity of 1 gram of carbon changes with time in the dead remains of once living material. It changes because of the radioactivity decay of carbon-14. So we can see that the activity has gone down from 16 to approximately 5 over the space of time of 9,000 years. Use the graph to show that the half-life, so we're using the graph to show that the half-life of carbon-14 is approximately 5,500 years, and you must show clearly on the graph how you get your answer. So it's not a matter of just reading off the graph, writing down an answer. You must show clearly on the graph how you get the answer. To do this, you need to use a ruler and a pencil. So we must use a ruler. Initially it tells us that the activity is 16 counts per minute. In 1 half-life, that will drop to half its original value, so 8 counts per minute. So we take our ruler and we draw a line from 8 counts per minute across to where it meets the curve on the graph. Then we bring this downwards as accurately as you possibly can and read off the value. and it is halfway between the 5,000 and the 6,000, so it shows that the half-life of carbon-14 is approximately 5,500, and I would write that value in, 5,500. So you're coming across from the half activity from the original. Half the original activity is 8, a horizontal line across to where it meets the graph, bring the vertical line down and read off the time in years. The next part of the question then continues along the same vein. In 1985, a human body was found in a peat bog in England. Archaeologists called the body peat marsh. The radioactivity of 1 gram of carbon from this body was measured and found to be 9 counts per minute after accounting for background activity. Use the graph to find as accurately as possible how long ago peat marsh died. So what we do is we go up to the graph and we take a horizontal line, find where 9 counts per minute is, halfway between the 8 and the 10, and draw an accurate horizontal line with a pencil and a ruler across to meet the graph, and then bring that line down to meet your axis. Now your pencil will be much sharper and have a finer point than my pen, so you'll be able to get a more accurate reading than I have. But where I see it comes across at 9 and it comes down, and I would read that as 4,600 years. Okay, you must show it. If you don't have the lines in the graph, you'll not get the marks for this question. So it's 4,600 years, and fill that into the answer box. You would get 1 mark for simply bringing the horizontal line across to 9, even if you don't read it accurately. You'd still get a mark for that construction line coming across and down, and then the second mark is for the accurate reading of the value at the bottom of the graph. This then continues on. Part 4. Calculate the activity of 1 gram of carbon from Pete Marsh's body 11,000 years after his death. So we don't necessarily need to use the graph this time because it does say calculate. Right, the half-life we found in the earlier question was 5,000 years. So 11,000 years after his death is 2 half-lives. And if we start off with a gram of carbon, the activity in the previous part of the question talked about the activity of a gram of carbon was 16. We can read that from the graph. This is the radioactivity of 1 gram of carbon. Starts out at 16 whenever it's new, and then it decays downwards. So the initial activity was 16. After 1 half-life, it goes down to half its original value. After the second half-life, it goes down to the quarter of its initial value. The initial activity is 16. The activity then is going to be 16 divided by 4. Let's remind ourselves why we divide it by 4. In the first half-life, it comes down to half of its original, which in this case would be 8. And in the second half-life, then it comes down to a quarter of its original value. So a quarter of 16 divided by 4 is 4 counts per minute. And you write that answer in there. The recognition of this point where 11,000 years is equivalent to 2 half-lives would get you a mark. Then calculating out that the initial activity is 16 and it goes down to a quarter of its original value would get the second mark, and then the final answer for the third mark. So 3 marks there. 1 for recognising that it's 2 half-lives, the second mark for realising that it's a quarter of its original activity, and the third mark for working out that quarter of the original activity.